Hello, and welcome back to our discussion on uncertainty in stage-discharge relationships. We will now discuss inputting stage-discharge information with uncertainty into HCFDA and evaluating with and without project conditions. Thus far, we have discussed the development of creating a stage-discharge function and attempting to define the uncertainty with a probability density function. The bounds of the PDF are defined based on engineering sensitivity analysis, and professional judgment. What we notice is that the stage uncertainty at zero flow and tends to increase as flow increases towards bank full stage. As flows get larger, the uncertainty may get larger or remain constant based on the shape of the floodplain. The probability density function can be represented through different statistical distribution. We are familiar with the normal distribution from a basic introduction to statistics, but there are other distributions that we can use to describe the stage-discharge PDF. Each distribution is described a bit differently. The distributions are a triangular distribution, which is a two-parameter bounded probability distribution function defined by the minimum stage and the maximum stage. A normal distribution, which is a two-parameter distribution function defined by the mean and the standard deviation. This produces a symmetrical bell-shaped curve applicable to many kinds of data sets where values are equally likely to be greater than or less than the mean. It's also called a Gaussian distribution. The distribution is truncated at plus and minus 3 standard deviations from the mean. The third distribution is a log normal distribution, which is defined by the mean and standard deviation. A non-symmetrical distribution is applicable to many kinds of data sets where the majority of values are less than the mean, but values greater than the mean can be extreme, such as with streamflow data. The distribution is truncated at 3 standard deviations. The standard deviation is computed by taking the logs of the stages from the sensitivity analysis and then subtracting the high stage from the low stage and dividing by 4 to get the standard deviation in log space. As hydraulic engineers, we prefer the triangular distribution because, as we discussed previously, we have more confidence in the minimum water surface profile and typically have less confidence in the maximum water surface profile. Therefore, the uncertainty distribution fits the triangular distribution better. When evaluating the uncertainty for your stage-discharge relationship, first consult this table of minimum standard deviations as taken from Engineering Manual 1110-2-1619. We have previously discussed a variety of methods for determining the standard deviation of error in the stage based on stage discharge rating curves or from computed water surface profiles using hydraulic modeling. Whichever method is used, the standard deviation of error generated should be checked against the table. The table is intended to provide consistency in core risk analysis and sets minimum limits that should be used when the computed values come out lower than the minimums. In other words, the values of standard deviation and stage errors from computed water surface profiles should never be less than the values shown in the table. The values in the table represent standard deviations of error in stage at design level discharges, for example, the 1% chance event. Standard deviations for events less than the design level will decrease as you go towards zero flow. Standard deviations for events greater than the design levels may be equal to or higher than what is shown in the table above. So if we take a look at the table, you'll see the data is broken up into Manning's N values, good, fair, and poor. Good meaning good field data, calibrated hydraulic model. Poor being estimated N values from poor data. And then we have elevation data from either field survey or aerial data such as LiDAR data versus poor elevation data from topographic maps based on various contour intervals. So you can see with high reliability in Manning's N values, with good cross-section data, we have a standard deviation of 0.3 versus poor reliability in Manning's N values and poor data, we have a minimum standard deviation of 1.5 feet. When entering stage discharge information into FDA with the probability distribution, Here you can see for the triangular distribution, we enter stage discharge information along with minimum and maximum water surface profiles. For the normal distribution, we enter the stage discharge information, but then provide a standard deviation of error for each given flow or stage. For the log normal distribution, we provide the stage discharge relationship along with the log standard deviation of error for each stage. Note that to use the log normal distribution, you need to compute the log of the standard deviation. The data has been entered into FDA. Summary tables provide output so that you can see the stage discharge functions along with the uncertainty limits. Here's a table, and here's a plot to get an idea for the uncertainty about a stage discharge curve. Now let's talk about stage uncertainty for with project conditions. Now that we have an understanding of uncertainty in computed water surface elevations, planning studies require that we apply the evaluation to study alternatives. Risk and uncertainty analysis can then be performed on the preferred alternatives. Generally, we're going to start with our without project conditions to develop our stage discharge ratings with uncertainty. We will then use that hydraulic model as the basis for developing our with project and our future condition scenarios for performing our risk-based analysis. Future conditions are likely to be more uncertain as we're uncertain as to what the future holds for land use development, building in the floodplain, the changing of the channel, etc. Existing with project condition may be less certain, but not always. For instance, with project, typically we have a better understanding of the design and how things will be implemented in the river system and may reduce uncertainty.